This is my 7th video about the best methods for reducing carboxylic acids to primary alcohols. This presentation will be about the use of samarium iodide as reducing agent. Samarium iodide is the only reagent known capable of reducing carboxylates in protic solvents by single electron transfer. Although other metals may be stronger reducing agents, samarium iodide, with a redox potential in water of -1.6 volts to -2.8 volts depending on the pH, is among the strongest known reducing agents soluble in organic solvents. Even Grignard reagents, organolithium compounds, or tetraaminoethylenes are not as strong electron donors as samarium iodide. So, this is again an instance where solubility of a reagent has a large impact on its reactivity, just like we saw with the ionic hydrides discussed in the first presentation of this playlist. When carboxylic acids are treated with alkali or alkaline earth metals, for instance while performing a Birch reduction, no reduction of the carboxyl group is usually observed. Thus, the Birch reduction of benzoic acid gives high yields of 1,4-dihydrobenzoic acid without any formation of aldehydes or alcohols. The examples on this slide are actually some of the few exceptions where reduction of the carboxyl group was observed. And even in most of these examples, no clean reduction occurred and mixtures of products were obtained. So, for instance, when undecanoic acid was treated with a large excess of lithium in ethylamine, a mixture of starting acid, an alcohol, and an aldehyde were obtained. And when 4-phenylbenzoic acid was subjected to the conditions of the Birch reduction, products resulting from a reduction of the carboxyl group were obtained in 25% yield. Therefore, the reduction of carboxylic acids by samarium iodide is a quite remarkable reaction. Interestingly, this reaction only proceeds in the presence of bases. It is assumed that the carboxylate reacts with samarium iodide to yield a carbon-centered radical, which is reduced in the slowest step of the reaction by a further equivalent of samarium iodide to the dianion of an aldehyde. The aldehyde is then reduced to the final alcohol by a similar sequence of single electron transfers. Critical for the success of such a reduction in the presence of water are the rate of the slowest reduction step compared to the rate of water reduction. Samarium iodide obviously reduces carboxylates faster than it reduces water. But even under aprotic conditions, not even lithium or sodium react with the carboxylate to yield the required carbon-centered radical. Only esters can be reduced by alkali metals, as realized in the Bouvard-Blanc reduction and the Acéloine condensation. Electrolysis cannot be used either to reduce acids in the way samarium iodide does, because the negatively charged carboxylate moves to the positively charged electrode and is oxidized to an oxygen-centered carboxyl radical, which decarboxylates and dimerizes. So, samarium iodide is a remarkable reagent indeed. The main advantage of samarium iodide as reducing agent for carboxylic acids is its ability to reduce acids in the presence of water. Many structurally complex natural carboxylic acids, for instance proteins, are difficult to dry or to convert into esters. With the discovery of samarium iodide, it has become possible to reduce such acids to alcohols. Reductions with samarium iodide are also exceedingly fast, what is again particularly useful for the reduction of large molecules where the concentration of functional groups will be inherently low. Reaction conditions are mild and the reductions are easy to perform. Unfortunately, samarium iodide is quite expensive, not only because of the price of samarium, but also because of the iodide and the fact that its synthesis requires diiodoethane or diiodomethane. Most reductions with samarium iodide require a large excess of reagent and accordingly generate a lot of waste. Therefore, catalytic procedures would be highly welcome, but have not yet been developed. In this example, a chlorobenzoic acid was reduced with an excess of samarium iodide in a mixture of water and THF. No reductive cleavage of the chlorine-carbon bond was observed. Remarkable is also the speed of the reaction, which attained completion in only 40 seconds. With this example, the configurational stability of chiral aryl acetic acids was to be tested, in the presence of samarium iodide. Despite the long reaction time, only little racemization occurred. This strategy can also be used to prepare alpha-deuterated alcohols. If the reduction is conducted in the presence of deuterium oxide instead of water, deuterium will be incorporated quantitatively into the alpha position of the resulting alcohol, as shown on this slide. Most of the potential side reactions of this strategy are caused by the high reduction potential of samarium iodide and the concomitant lack of selectivity. Thus, a number of other functional groups are readily reduced, such as olefins, benzyl alcohols, ketones, various carboxylic acid derivatives, epoxides, and reactive alkyl or aryl halides. Even some types of cyclopropane may undergo reductive cleavage. Because aldehydes are formed as intermediates during the reduction of carboxylic acids, these may dimerize to pinacols if too little samarium iodide or solvent were used. To conclude, samarium iodide enables the reduction of carboxylic acids in water, but a large excess of reagent is usually required. Therefore, this reducing agent can realistically only be used for the preparation of expensive alcohols and for laboratory preparations, where costs and waste disposal are a minor issue only.